these are available on developer.qualcomm.com. Today we're going to cover two major topics. One, Vulkan, as has been mentioned, and the other is we're going to go through several real-world use cases for using our Snapdragon profiler to optimize apps and understand the performance of various applications. Vulkan. Anybody familiar with Vulkan? Fair amount. So the two sessions we're going to go to, one is the performance profiling, the second is a really deep dive into Vulkan and the capabilities that are going to be on devices shipping this year. Carlos will be covering the profiler use cases. Dan will be covering the Vulkan stuff. Really quick though, if you don't know what Snapdragon Profiler is, it is our system profiler tool. This allows you to understand what's happening on the CPU, the GPU, the DSP, power performance, thermal performance, networking data, memory usage, bandwidth, etc. We have designed this with VR, mobile VR in particular, becoming or having a much bigger presence here now and into the future. Snapdragon Profiler is designed to help you understand performance of VR apps. And that's some of the stuff that we'll be going into today. You can use this tool with any Snapdragon powered device. You do not need to have root access to use it. You can use it with your commercial devices. And it's comprehensive. Real-time data, trace data, you can do frame captures if you're a graphics developer. So pretty extensive tool. Carlos will be kind of diving into that. They mentioned a few of these things here. We do support the major host platforms, Windows, OS X, and Linux. For the GPU APIs, we have OpenGLES, OpenCL, Vulkan support. One caveat with the GPU is it will only work with Snapdragon 805 and newer chipsets. But it's a very powerful tool and will help you understand both VR, Vulkan, and pretty much any other major technology coming out here in the future. So with that, I will hand it over to Carlos to go ahead and dive into some of these use cases.
Maybe I'll just use the microphone. Let's see if I can make that work.
Okay. So yeah, like Kevin mentioned, I'll be using Snapdragon Profiler to debug and analyze three scenarios. Instead of me just like going like an overview of all the Snapdragon Profiler features, I wanted to really try to use an application that would show like things that you would probably bump into in the wild. The first application that I'm going to be looking at is VR application, since VR is the hot topic right now. For this application, what's interesting is that it's an application that I just downloaded from the Play Store. I do not have source code for it, and I just downloaded it and tried to look at it in Profiler, see if I could find any bottlenecks, what potential improvements that I could find. So, our goal for this application is going to try to find areas of improvement. All I'm going to use is Snapdragon Profiler, and I'm going to be using a Nexus 5X, not rooted, like Kevin mentioned. And so before I actually dive into the application for profiling graphics applications, we kind of want to understand a little bit better what tiling architecture is, which is what our GPU is based on. Does anyone know what tiling architecture is for a GPU? Okay, cool. So then this looks a little more daunting than it actually is if we actually go a little by little. But it's basically the way that things are actually rendered in the GPU. Let's go little by little. We have this one thing called the frame buffer, which is what is actually going to be displayed into the screen. And then we have things that we want to be rendered, which are our triangles that make up the meshes. So what a tiler, or a GPU with a tiler architecture does, is the first thing that it does is tries to calculate bins that it's just a primitive that it uses for optimization purposes that we're going to talk in the later steps. So basically, it grabs that frame buffer and split it up in bins. Once it does that, it grabs the vertices of the triangles that you're going to be rendering, and it's going to transform them into the positions based on the viewport from where you're looking at. And then it starts creating what's called a visibility stream. So basically, it first tries to go drawcle by drawcle, and then gets like the first drawcle, and for each one of the bins, it calculates which bin actually contains that triangle. So in this case, we can see that only the first bin has a triangle, and then the other ones don't have a triangle. Then you keep going. We have a second triangle, and then that one appears on this bin, in the first bin, the third bin, and the fourth bin. So once we have our visibility stream created, assuming we only have 2 triangles, one thing may or may not happen, and this is actually going to be the focus of this first demo, but a tiler GPU has the graphics memory that is on the chip. It's very fast, but it's very small. So that is why we actually need to bin things, because we need to grab each bin and put it in the graphics memory to be able to calculate the shading and painting pretty pictures pretty much. So one thing that could happen is that this frame buffer that we have needs to get loaded into the graphics memory so we can render to it. The reason why I'm saying that it may or may not need to happen is because if there's nothing on it, we should need to copy it into the graphics memory. But let's say that it does happen. It doesn't really matter right now. So after that, we for each one of these bins, we grab their visibility stream. We start rendering our primitives. It goes to the rasterization, which puts it in the screen coordinates, and then it calculates Z test, alpha test, fragment shading, blending, the layers. And basically, once we have the color, it writes it into the GMEM. So then after that, once we have our tile rendered, it gets stored back into the main memory. And that is what is called a GMEM store. Just so that we start thinking in terms of nomenclature, it's GMEM load and GMEM store. Then after that, if this is not the last bin, then we go through all the other bins and do the same path over and over again until we finish with all the bins. If this is the last bin, then we just present this image to the screen. So it's not as daunting as it probably looked like when I had just everything uncovered. So with this in mind, and like I said, I'm going to be looking at what a GMEM load is. The problem with OpenGL, and it's one of the things that Vulkan is really good at, is that Vulkan is much more explicit, and OpenGL actually, it's much farther away from the hardware, so sometimes you don't know what it's actually doing underneath, and sometimes you can do something that you didn't intend for it to do, like in this case a GMEM load. So let's look at what could happen. So, if you look at what we have there in the wrong way, if you render to this back buffer, and then you render to an FBO, to a buffer, and then you try to render back to the mainframe buffer, when you try to render again into the mainframe buffer, the mainframe buffer already has useful content, so it's going to actually force, the driver is going to force load this memory from the main memory to the graphics memory. the right way of doing this would be to actually render it to your frame buffer object first, and then you render to the back buffer, to your screen, and you will not see this. This can happen because OpenGL has hints that the driver needs to know. So for example, if you call an EGL swap buffers, which is the call that presents something to the screen, and then you don't clear the buffer right after that, when you start drawing to it, the GPU will think that you care about the content from the previous frame, and it will reload this information back into the GMEM, causing a GMEM load. So that's one case, but there's other cases. I actually put a link here for the Adreno developer guide, which has more information about these and other optimizations that you can do when you're doing graphics programming. This diagram is actually from the Adreno developer guide, and it will show all the cases where a GMEM load could happen that it's actually completely unnecessary if you didn't intend it to happen. So, that's it. I'm gonna go to Snapdragon Profiler. So this is Snapdragon Profiler. It's like Kevin said, it's kind of like a one-stop solution for profiling across the system on a chip. And like I said, all I need to do is use the Nexus 5X, and all I need is enable Android debugging, which I already did. And first thing I need to do is just connect to the device. So we'll see that the device shows up in here. We connect to the device. So while it's connecting, there are three main capture modes in Snapdragon Profiler. We have real-time, trace, and snapshot. For the purposes of this first demo, we're going to be using trace and snapshot, and I'm going to explain more about what they are while I'm using them. I just wanted to briefly introduce real-time. I don't necessarily need it for this demo, but it's good to know. And this is actually probably like the first place that I usually start when I'm trying to look for bottlenecks or trying to analyze something, because we have both per process and system-wide metrics that we could use to see if we're GPU bound or CPU bound, or even like Kevin said, we have thermal, power. You can see them, network, all sorts of metrics. So let me open my app, and then we'll see that in the process list on the left, we'll see. Okay. Let me just click through the ads, of course. Okay. So now I clicked on the app. We have some per process metrics. We could add some CPU utilization. I could add some frames per second just to get an initial idea of where we're at. I could grab the utilization that's per process. We could actually see utilization per core. With these, I can actually change the graph mode just to make it easier to read. And we can add all sorts of metrics. I encourage you to download Profiler and then just looking at them and play around with what they are and what they do. But anyway, so for this capture, the reason why I'm looking at GMEM loads is because they can be a low-hanging fruit optimization. So in some cases when this happens, literally there's just something very simple that you need to do, maybe even just like a one-liner, and boom, they're gone. So in this case, how would we go about looking for GMEM loads? So first we need to know what tool we would need to use to look for GMM loads. So in Profiler, we have a metric that we call rendering stages, which I'll actually backtrack a little bit because that will explain a little bit more what rendering stages is. So we looked at the Tyler architecture, which so we see that there's many phases to rendering triangles. So one of them would be the binning pass, there would be the rendering pass, and there would be the result pass, which would be either storing to the graphics memory or perhaps having to load to the GMM, which is another pass. So within Snapdragon Profiler, there is a metric called rendering stages, which basically you can use to see what stages are actually active at each point in time when you're rendering your application. This metric is actually on our second capture mode, which is a time-based capture. You start and stop a capture. And it's similar to systrace, what you would see on the systrace profiler, which we actually do grab the same systrace data and we can correlate with our own metrics, in this case the rendering stages. So again, I look up for my process, I click on it, I see the metrics that I have available for my process. In this case, I need to go to the OpenGL tab and I'll see rendering stages. Then I start a capture, I stop a capture, wait for the data to come in, check for the data. So, what are we seeing here? We're looking at a Gantt style chart, in this case with rendering stages metric. What this shows us is all these phases that I just talked about. We see a binning phase, a rendering phase, GMM store, GMM load, and we see what's actually happening on the GPU while this is being rendered. Just to make it clear, this IV start marker, it's what's called the instruction buffer, and this is actually what gets submitted to the GPU. So with these, we can actually use them sort of as a frame delimiter. So we can see that from here to here, we have a frame. Now, what we're looking for here is GMM loads, right? Because if we find GMM loads, there is a possibility that we can just get rid of them very easily. In this case, bam, we have a bunch of GMM loads right here. I don't know if you can see them very good with the projector, but actually probably if I can close it. So, also we can see that if we can get rid of them, they take a significant amount of rendering time from the overall rendering of a frame. And we know that for VR, that's very important because we want to target at least 90 frames per second. So now that we know that we have GMM loads, we need to start to try to understand why are they happening, and to know why are they happening, we first need to know how is this app actually working and how is the frame being constructed. So above the rendering phases, we also see a track that is called the surfaces. So this is actually the surfaces that the geometry is actually being rendered to. And then we can see the dimensions of these surfaces. So this is 960 by 1080, this is 1080 by 1920. Then this one, again, it's 960 by 1080, 960 by 1080, and 1080 by 1920. So just from the looks of it, at least to me, I guess, it's pretty obvious that this is the resolution of the screen. So this must be the buffer that is being rendered to composite the actual final frame because of the size of the screen. And this looks exactly like half of it. So this, being a VRM, I could guess that this is an eye. It is rendering to an eye. So we can start to try to construct in our heads how this frame is actually being rendered. It's rendering to an eye, then it renders it to the back buffer. At least that's what I think. We've yet to confirm this hypothesis. Then we switch to the other eye, we render the other eye, and we render to the back buffer. And then the frame stops. So how can we, I guess, make sure that this is right, what I'm saying is right. So we have the third capture mode, which is called Snapshot. And the Snapshot mode is a heavyweight capture mode. What it does is basically, it grabs everything from the GPU context, being shaders, textures, draw calls, buffers, everything that was done to make up the frame that we captured, and present it to the profiler. So I can go back to the start page or go to capture, new snapshot. Again, I go and find my process. And take a snapshot. Snapshot is, like I said, is a heavyweight operation because it grabs pretty much everything, including all the textures, so it tends to take a little bit of time. But we will get some data that we can work with while this snapshot is actually happening. So this is the app. This is actually facing down because I have the phone facing down. I apologize, I probably should have done facing forward, but this is basically what Profiler Snapshot would give you. It gives you a screenshot of what it actually got captured. It will give you all the draw calls that were executed to create this one frame. And then once we get all the data, we will get all the textures, all the buffers. There we go. All the textures, all the buffers, pretty much everything that was used. Yes?
Is the app running in the background right now?
No, the app's actually running right here on the phone. So I just opened the app, I selected it there, and then just say, okay, capture a frame that we want to analyze. So these are all the draw calls that were done to create this frame. What we want to look for is what could have caused these gmem loads. So I know that gmem load can be caused by us switching frame buffers without, but basically us switching frame buffers. Let's just leave it at that. So how do we switch frame buffers in OpenGL? We use GL bind frame buffer. That's the API call that we use to change frame buffers. So in Snapdragon Profiler, we have the Data Explorer, which is the one that is the view that will give us all these draw calls. Within each draw call, we'll see all the API calls that were actually done that led to that draw call. So basically, all these calls actually happened before that draw call actually happened. And that gives us insight on what state in OpenGL actually changed before we actually created that draw call. So, Profiler has a filtering functionality that will help us find these GL bind frame buffers really quickly. So I can just start typing GL bind frame buffer. So we see that it happens in 5 calls. Just to give you an idea, so you get a better idea on like where we're at within the frame. You can look at this ID number here, and that's where you're at within the full list of calls that actually happened. So we can see that the first thing that happened is we bound to the frame buffer 0, which is what OpenGL does to render to the back buffer that actually gets presented to the screen. And it clears it. That's all good. then it goes to this secondary frame buffer that it just so happens to be frame buffer 2, and then it clears it. Then it goes to the main frame buffer, and it draws some things. Then it goes to that secondary frame buffer that it just happens to be frame buffer 2 again. It clears it, and then it goes back to the main frame buffer and draws something. We don't know what's that something yet. That's what we want to find out. So let's go little by little. We bound this secondary frame buffer and we cleared it. That's fine. Then what I'm mostly interested is in this code here, because it's the one that is rendering back to the main frame buffer. Let's remove this filter, and remember that is draw call 35. So let's look at what happened right before that draw call. So Snapshot mode will actually give you something that is very educational, because you can actually do a capture up to a certain point within the draw call list. And that will help you see how the frame is actually being constructed. So I can actually double click this draw call, and what Profiler will do is will actually recapture that one frame up to that draw call, and then present it to the screen. And it's shown in there. So we can see that right before draw call 34, we render what it looks to be the view from one eye. Then I can look at draw call 35, which is the one that actually binds back to the back buffer, which is the one that gets presented to the screen. And we wait for the screenshot, and then bam. Okay. So now we can see how draw call 34 renders one eye, draw call 35 goes back to the back buffer and renders that eye into the back buffer. Then, so far so good, we rendered one eye. So let's see what other buffer changes, happened. Okay, so we know that draw call 35, which is the one that we just rendered here, switched back to the main frame buffer and rendered that one eye. Draw call 36 goes back to this secondary frame buffer that we have, and then draw call 69 goes back to the main frame buffer. So let's do the same thing for draw call 69 and see what's going on. So let's look at what happens right before we bind back to the mainframe buffer. And as you might guess, it's going to be rendering the second eye to this secondary frame buffer. There we go. So that's the second eye. That's the last call that renders to that second eye, which, if I remember correctly, it's the cursor. I think that's the last thing. There you go. Just the cursor, the last draw call that renders to that one eye. And then we look at draw call 69, which is the one that renders back to the mainframe buffer. And let's see what happens. So it renders the second eye, right? So now we get an idea just by looking through the draw calls how this frame was actually constructed. We know that it rendered to the secondary frame buffer, it rendered one eye, went back to the back buffer, and rendered it to the back buffer. Then it did the second eye, and then it rendered it back. Anybody see an issue here so far? No? Let me go back to PowerPoint a little bit. So like I said, this is pretty much what we just discovered in using the snapshot view. We render to one eye, we render to the mainframe buffer that one eye, we render the second eye, and then we render the second eye. Still no red flags?
So I would assume that you are drawing twice the same thing.
So this is actually, well, the two eyes are actually different renders. That's fine. But if we go back to this frame, this slide, we see that, does anybody see any similarities with this and what we just saw?
So you're doing it wrong.
They're doing the wrong way, right?
Yeah.
Okay, so since should I do that? I don't know, that is not sure. Well, we'll talk later, but you'll be able to choose one of the giveaways that we have. Yeah, we're doing the wrong thing, and where are we doing the wrong thing? Is the wrong way of doing this is we render to the mainframe buffer, then we render to an FBO, and then we render to the rest of the scene to the mainframe buffer. So let's go back to how this is constructed. So when we look at the rendering the left eye, that's fine. When we switch back to the mainframe buffer and render that eye, that is fine too. That there's no issue necessarily in there. Then we render to the second eye, to the right eye, still all good. But then we render the second eye into the back buffer. So what's happening here is that the back buffer already contains some data. So the GPU thinks, oh, this buffer already has some data in it. I need to put it in the graphics memory so I can even render the second eye. And that operation is very, very expensive, and that is exactly what we're seeing in this trace capture. So, any questions so far? Huh? Okay. So, going back to the profiler, we'll see that, well, going to the trace, that is pretty much what is generating everything here. And why do we see so many? Because this is for every bin that we render, we incur into a genome mode. Because for every bin, you need to reload it from main memory to the graphics memory. Very, very costly. What could be a potential solution here? Any?
Render the left and right eyes to two separate off-screen surfaces, and then...
Perfect. Yeah. So just switching things around could potentially be a solution. You get another gig. Yeah. So just switching these two, then yeah, you might now incur in a little bit of overhead by fetching data from the texture, but it's nowhere near the amount of overhead of actually loading that into the back buffer, into the genome. So that. What's that? Okay. So I'd rather keep this use case and maybe I'll switch to the fracture, and then I'll also just the card demo. So yeah, I'm running low in time, so I'll wrap up one more thing that I had on this use case, which I find it very interesting because I just found about it yesterday and it blew my mind. So I'll share it with you guys, and I'll skip the second demo and I'll go straight to my third demo. So I just want to go back here to Profiler and show this again. So just by doing this solution that you proposed, that would get rid of these genome nodes. So when I was looking at this capture and looking at how we finally verified that, yeah, we're rendering to one eye, rendering to the back buffer, rendering to the second eye, rendering to the back buffer. All that's good. We could get rid of these GMM loads. But what started to trouble me is that I started to find more GMM loads in the second eye. And I couldn't quite understand why that was happening. I looked at the draw calls, and all I see is that here we're rendering to the back buffer, and then we switch to the secondary frame buffer. So I went back here and then looked at what all is happening when we switch back to that eye to the secondary buffer to render to the second eye. So here's where let's go back to the beginning. Here we switch to the secondary frame buffer to render to one eye. Then this is the one that renders that one eye to the main frame buffer. Then we switch back to the secondary frame buffer. We clear it, and then we render to it. But what troubled me is that if you look at draw call, well, at the call 36, which switches back to that to the secondary frame buffer. So GL clear switches back to that secondary frame buffer. Nothing really happens besides just more draw calls. Like there's no more binding of frame buffers or anything. So I was like, why is this? Well, I saw that these GMM loads were added, but also like I didn't quite understand why there was this guy here. What's rendering here? Because there's no binning. The fact that there's no binning, that means that there's no draw calls, because no visibility streams were created. So after looking at it a little bit, I was like, okay, so what's happening there? So all I could think of is that GL clear, it's the only thing that's happening before the draw call when we switch back to that second eye. And when I did a replay, I realized I bumped into this, which may look like, okay, this is a GL clear, okay, that's fine and dandy. But what made me like eureka was, the eureka moment was like, it's rendering to a color. What if rendering to a color is just causing the GPU maybe the GMM itself doesn't know how to handle rendering to a color, and it needs to somehow load the frame buffer into the GMM to render this color, and then when it starts rendering draw calls, it thinks that it already has data, even though all it has is a clear color, and then it causes all these GMM loads. That was my conjecture. So now I had to prove it without any source code. So I used another feature that we have in Profiler, which is invaluable for like debugging issues, graphics issues, which is overrides. So we can actually override things that are happening within the device in real time and then recapture. These overrides are actually within the options tab. You can go to the combo box here and then you can see GL real-time overrides. And I have all sorts of overrides. Like I can override all sorts of modes from the state of OpenGL. So what I'm mostly interested in here is I have an override that's called disable clear colors. So if I disable all clear colors, nothing is going to clear. My frame is going to be all screwed up. But I'm saying that the clear color is the one that is causing this extra pass. So if I can disable that and I don't see that extra pass, it's because that clear color is indeed causing this extra pass that I shouldn't have. So I enable the override, You can't actually see it here, but the rendering is all screwed up because it's not really clearing anything, so it just keeps buffering and buffering and buffering. And I capture again. So the first thing to note is that within one frame, everything has a Gmail load. Why? Because I disabled clear colors, so the GPU thinks that everything is important from what was rendered from previous frames because I didn't clear it. So everything has Gmail loads. But that's not the important thing here. The important thing here is that I disabled GL clears and that extra path disappeared. I only have what I expected, which is render to one eye, render to the back buffer, render to the other eye, render to the back buffer. So just changing that clear color from a color to black would save me this amount of time of the frame. So again, I have no source code. Just by looking at what I can do within Profiler, I came to that conclusion. So that's about it in terms of like this demo. Now, because of time constraints, I'll just bump into the other demo that I want to do, which is a Vulkan capture, just to show our profiling capabilities. I forgot to go. I'm sorry. I apologize. I didn't grab my device in time, so you want to set up while I start talking about that? You can just. So any questions so far, by the way?
Yeah, so you mentioned that you can connect the device and you obtain the information through this trace?
So you mentioned that you connect the device and you start obtaining this data through systrace, or is that a different call through ADB?
It's a different call through ADB. It's our Snapdragon profiler data.
Is there any like public API that anyone could use? Because I would love to use this on CI example.
Yeah. Okay, yeah. There you go.
Question right here?
This is after this. One of the things we start recognize is the OLED panel on the VR is when you output the buffer, it actually scans 4 different times. So when you render the first one, don't you have to be able to ship that thing out to the display already?
If I understand correctly, I think you're talking about yet another optimization for VR, right? That when you're scanning, you want it to render the first eye.
Because on the Samsung panel, they have limit buffers. You cannot scan the whole frame anyway. So that is only, compare the GPU side from the UK, they cut it down to 4 pieces and ship it to the panel. Because they load it to the panel first, and they have 1/3 memory in the panel. So they pop one core screen, one core screen, one core screen, one core screen. So in that case, you can remove the load and the frame buffer out the door first. You don't hold it.
Yeah, I wouldn't know about.
You can take that offline afterwards.
Okay. Yeah. Let's take it offline because I mean these bins that I'm talking about here, we don't get any information like from the display to actually compute the bins. The bins are actually computed based on the size of the frame buffer and the size of the graphics memory. So for example, if you use multiple render targets to render, you'll have smaller bins. But I don't think it has any information in terms of the type of display, at least at the driver OpenGL level, right?
Introduce. So, welcome to Mobile Monday. My name is Mario Tapia. I want to also introduce Andrew, who's also managing the space here tonight. If you guys were curious, how many people here first time at this venue? Yeah, you know what the hell is this place, and where are the offices? Yeah, I mean, so maybe Andrew can explain that.
Yeah, you're not the only one to think that. We get that a lot. People come in and they're like, "This, I don't see any cubes. What's built here?" Nothing is built here specifically by Microsoft. It's a community space, so we host cool things like Mobile Mondays, other data talks, VR, AR, gaming, kind of the whole gambit. Everything runs on Azure, so we kind of encompass that whole ecosystem here. So if you have an event, something that you're interested in running, feel free to come talk to me. If you want to find out more about the space, you can go to microsoftreactor.com. There's a little calendar there that kind of shows all our upcoming events and what's happening in the space. Housekeeping things, maybe you've already found this, but the restroom is back in that corner. So if you're wandering around, that's where it's at. But yeah, feel free to come talk to me afterwards. We also have cool programs for startups and other stuff that we're working on.
How do I get to work here?
Yeah, so if you want to work here, we're just in the next couple days, you'll see something come up onto our website that's going to have a couple, like 10 or so questions about your startup, what you're working on, kind of what your needs are for space. And then from there, we'll start a discussion and dialogue and see if this is kind of the right place for you to be sitting. Definitely don't have to be working on Microsoft tech. If you're working on something really interesting, we're open to kind of all potential startups working out of here. Just kind of filling that out online to get a good idea of what you're working on, and then we'll go from there.
How are you guys doing over here?
Hi, I'm Dan Archard. I'm also from Qualcomm, and I'm going to talk a little bit about Vulkan. I've called it Impractical Vulkan because I work for a hardware company, and a lot of our recommendations aren't really practical for your app. But in an ideal circumstance, hopefully you'll get some value out of this. So there's already plenty of samples out there that talk about Vulkan, so I'm not going to go over any like how to use Vulkan stuff. I'm going to give some general advice about how to manage memory and why you want to do that, especially on Qualcomm hardware. Sorting based on PSOs, some SOC chain management stuff, because a lot of the samples do it incorrectly, and if you just copy the sample, you're not going to get the best performance. How Vulkan features map more directly to the Adreno 530 GPU, which is the latest Qualcomm GPU that's in the Galaxy S7. A lot of people say that Vulkan's tiler friendly, so that's sort of what I'm going to get into. As well as some forward-looking features that take more advantage of the hardware that you might want to use. So a little disclaimer, this is very Adreno 530 specific, on 2016 devices. What works for 530 may not work for future devices and may not work for backported devices if they support Vulkan. I'm not really going to get into any NDA specific secret source stuff. There will be things that we haven't talked about in the public as much, which will hopefully be useful because you kind of need to know more about the details to get the best performance when using Vulkan. So I will get into that a little bit. So I am sorry that I won't like give you real values. It'll just kind of be like hand wavy, 10x, stuff like that. And tomorrow, all this advice could be completely invalidated because the driver's new, the technology's new. We're still feeling things out and trying to understand like the best way to use Vulkan on the hardware. So, jumping into general advice, we're going to go with memory management first. So, this is not really a code snippet, but basically that's how you allocate memory in Vulkan. You get the memory requirements for the buffer that you need, you allocate the memory, and then you bind it to your buffer. Right? It's simple. Oops, what have we done? Alright, nothing new. We're not actually talking about how to allocate memory in Vulkan, so what's interesting about this? Well, allocated memory on Qualcomm hardware allocates page-line memory. Right, that happens on a lot of devices, especially Windows. But for us, for Qualcomm, we have very, very large pages. What does that mean? So on some other hardware vendor, you might expect page line memory to allocate on a 4K boundary. This is our page size for comparison. What does that mean? You're going to run out of memory very quickly if you do a lot of little allocations, and that's not what you want. So you really need to think about memory pooling and how you're going to pool your memory. Now, on our GLS driver, it does always work for you. So it'll allocate big blocks of memory, and it'll have like a little memory allocator that'll allow you to do smaller allocations, and you'll be happy, you'll be fine. And only run out of memory when you actually hit the memory boundary. This, you're going to internally fragment all your memory, run out really fast, even on a 3 GB device like the GS7. So, the rough recommendation at the moment is to allocate large blocks of memory based on the properties that you need for your buffer, and then set up your allocator to allocate out of those. So pretty much what you want to do is you want to have this little allocate memory function that will give you an offset into the buffer, the big buffer that you've allocated for your memory type, and then you have some way to index into that from the pool, which will actually return your VK device memory, and then you'll be able to bind that memory to the buffer that you want. Don't really have time to sort of get into a deeper analysis of what you need to do, but this sort of gives you a rough idea of, or hopefully a rough idea of how you can sort of set up a pool-based allocation and bind it to your resources. Any questions about that? Okay. So the next bit of advice is sorting on pipeline state. In the past, on the 4X series and the 3X series, we've recommended drawing front to back. This way, when you're rendering, you don't have to worry about overdraw as much because you're able to do like a quick depth cull for the pixels that have already been rendered to the front. For A530, we don't need that. We've got this thing that we call Advanced Draw Order Independent Rejection. I didn't come up with the name, I just have to use it. But basically, depth rejection happens now before the fragment is shaded. So you don't have to worry about sorting based on depth, you can now sort based on your pipeline state object. What this means, why would you want to do this? On our hardware in particular, the reason we want to do this is for every tile that's actually rendered, and Carlos talked a little bit about that, but every state change and draw is processed for every tile. So if you have 4 draw calls with 4 state changes, they're actually running every tile. Now, whether it actually falls inside the tile or not, this is going to happen. So I'm going to talk a little bit about this in a minute. It doesn't really make much sense, but I'm going to hopefully clear that up with the next slide. So if we've got this really sort of simple scene where we're doing 4 draw calls, and then these are our different tiles. We've split the scene up into 4 tiles based, it's completely arbitrary, which is good for this example, but it's based on the frame buffer depth. And then from the application, we've set the colours here, the pipeline state objects, just a nice easy way to represent it. So we're going to set the colour to draw 0, set the colour to draw 1, etc, etc, etc. So what does this actually look like when we're actually rendering to the tile? So when we get to the first tile, now the order of the tiles are rendered are completely arbitrary. Here I've gone from left to right, I'm just going to do the first 4 as an example. But so when we render tile 0, when we process draw 0 is not actually in this tile, so that's what we call a dead draw. But it's still processed. Now, when we get to draw 1, that's actually in the tile, draw 2 is not, draw 3 is not. So we've actually processed all 4 draws and all 4 state changes just for this one little object. And then as we go through, we see it's the same for the next tiles. So I didn't explain that green is a draw call that's actually drawing something, green is a dead draw call that's not drawing anything. So if we go through the last one, we can see that draw 3, there's 3 dead draw calls to start off with, and then we actually have a draw that hits the tile in the 4th tile. So what this basically means is that if you're switching states a lot, which is okay, you can, but you're going to accept that you're going to take that overhead per tile. So I don't really explain this very well. If you're going to switch between state backwards and forwards, you're going to incur that overhead per tile, whether it's being rendered or not. That's far cheaper on the GPU to actually sort based on pixel state and then take that state change once per tile and then do all the draws. The dead draws are still fairly cheap. There is some cost there, but it's still fairly cheap. So some more general advice on pipeline state stuff. if at all possible, try to use derivative PSOs. I don't think that's really realistic because the dynamic nature of scenes, you can't really know what state's going to come after what state. You're probably going to spend more time on the CPU trying to sort all your states so you can make use of derivative PSOs. And in that case, you're probably going to have to generate the derivative PSOs on the fly, so you're going to stutter. So I don't think it's actually that useful, but if you can ever find a use for it, there is a small benefit to actually using derivative PSOs. And if you can, prefer not to use dynamic states at all. Descriptors. Revalidating around descriptor sets is actually the most expensive thing that happens in the driver. If you can, keep them small. That will keep the update time down, and there'll be a little bit less overhead time in the driver. And use push constants if you can. If there's any data that fit in them, and you've got a significantly sized draw call, use a push constant. The significantly sized draw call will actually disguise any overhead required to write that data from their front-end processor to update that with push constant. I'm actually moving through this pretty fast. Swap chain management. Like I said before, all the samples do it wrong. I haven't checked some of the newer samples. They may have actually fixed it, but basically they're submitting the queue and then waiting for it. You don't want to do that. That will add a synchronization point between the CPU and GPU every frame, and you're basically wasting time. The GPU is going to sit there and wait until you come back around the next frame and actually submit your work. So I don't know if you can read this, it's pretty small. So this is a better example of what you want to do. This is actually example 5 from the Vulkan spec, Vulkan Plus WS1 spec. What it is actually doing is it is keeping fences for some number of frames that you will allow latency to happen, so if the GPU gets in front of the CPU before you'll actually stall. And then, so you'll have enough buffer space to be able to sort of run away and then just let the GPU go until you've run out of fences, and then you'll have to stall. Now, hopefully that'll never happen. So in Protostar we use 3. And that seemed to work pretty well for the GS7. You may need to use more. It just really depends on how much latency you want and how much work you're actually submitting to the GPU. Alright, so support for tiling hardware in Vulkan on A5X. There's three things that I'm going to talk about here. I'm going to talk about subpasses, what we call multipass, and then subpass region, which you may not have heard of before. So render passes are the only way to render anything in Vulkan, render to a frame buffer. We prefer that you use subpass contents in line. That allows you to take advantage of this advanced draw independent rejection that I talked a little bit about earlier. And something to keep in mind with render passes is that a frame buffer in Vulkan isn't the same as a frame buffer in GL. GL only has the attachments for the current rendering pass. Vulkan, you attach all the attachments that you want to render to for any potential subpass. I'll talk a little bit now about how you realise that. So this is the G buffer from Unreal Engine for a demo that they showed at GDC in 2014 called Infiltrator. This is actually captured on the PC, but it sort of highlights the example pretty well. Now, you can see here I've just arbitrarily split it up into 24 tiles. We've got quite a deep G buffer here. There's 2, 4, 6, 7 attachments. Well, there's actually 8 because there's stencil, but you can't see that because it's inside the depth. So we are going to end up with much smaller tiles than, say, if you were just rendering to a 32-bit color frame buffer with depth. This one here that you can't really see is the scene color, normals, and then there's a bunch of other properties, and then depth. Now, if you're familiar with Unreal Engine at all, Unreal Engine does the deferred render, it does an opaque pass, and then at some stage later, here I'm going to pretend like it happened straight after, it will do ambient occlusion, and then it will apply that ambient occlusion on top of the scene color. So, in GL, or DirectX, when UE does the ambient occlusion pass, it takes this normal buffer and the depth buffer, and then generates as output the ambient occlusion pass. which is then applied on top. You can't really see it very well, sorry, on the projector, which is then applied on top of the scene color. It's still fairly dark, as a lot of the other sexiness hasn't been applied yet. It's pretty early in the render. Now, in Vulkan, the Vulkan frame buffer, if you were to try to do this in the one render pass with multiple subclasses, you would actually attach all of these attachments as well as the AL output. And what that means is you're now going to have a much, much deeper frame buffer, so you're going to end up with some number of bins that are actually smaller. So the reason subclasses are useful is because it gives you the functionality that was available in GL called shaded pixel level storage, which is actually an extension from ARM that they came out with a couple of years ago. Shaded pixel level storage allows you to pass information from one render pass to another and then sort of apply that back on top. But it has to be the same pixel. There's sort of no way to branch out from that pixel. The Vulkan way is subpasses with subpass load and input targets. Now, why is this important, and what is cool about it on tiling hardware? So if we look at a GL version of the render passes we just looked at, we have the opaque pass, and then in this sample, these are draw calls. There's an arbitrary number of draw calls during the opaque pass. We split the scene up into bins. There's 26 bins from 0 to 25. So we'll render the number of draw calls to this bin and write them out as the G buffer that we saw, the ones that are interested in the scene color, normals, and depth. So everything will get rendered to bin 0, like colors talked about, then written out to RAM, and then we'll continue on through that. Now, when we get to the AO pass, we have to read the normals and depth textures that we just rendered in the last pass as part of the AO pass through the texture engine. And then we're going to render those to the 4 different bins that we saw before, and then we're going to write it out again. And then we're going to read it in again with the scene color, but because the way Unreal Engine 4 applies the ambient occlusion on top of the scene color, it's not reading the scene color as a texture and applying it for the ambient occlusion, it's actually blending it over the top. So we've got that information that we need back into GMAN to blend on top. So these big red lines here are doing the GMAN load that we saw before back into GMAN. And then we're also rendering in we're also reading in from RAM the ambient occlusion texture, and then we're blending that together, and then per tile, running it out again. Now, if we look at it with Vulkan and subclasses, we can do this. Notice this is those entire 3 passes in one slide, and there's 2 DRAM accesses rather than however many we had before, and no GMAN loads. So we can do the opaque render pass, the AO render pass. This is reading the scene color, and the normals and the depth, and then we're rendering out the AO, then we're reading it back in again, and then writing it out, and then finally writing out the scene color with the AO applied. So the writing to GMAN is roughly 10 to 12 times faster than writing to DRAM, and also uses a hell of a lot less power. So ideally, you don't want to do many RAM access, many system memory accesses at all if you can get away with it. You'll run longer, you'll run cooler, you'll run faster. This is the ideal situation. Now, when using subclasses, there are a few caveats. You don't want to use input targets unless you're actually planning on doing multipass using subclass load. It may work, but the driver has to do a bunch more management, and you're going to hear from Zach over here if you do it, because he's going to have to figure out why you broke the driver. Don't put a bunch of unrelated subclasses into a single render pass. This is not multipass. What you're trying to actually do is have separate passes for some reason with subclasses. The driver then has to try to figure out this sort of graph walking problem. It's not fast. You wanted a fast driver that's dumb. Now you're asking it to actually do something smart. Please don't, because you'll actually get a faster driver if you don't do that. And also set up your subpass descriptor correctly. Hopefully this will be online so you'll be able to see it. But these are the properties that you actually want to set up with your subpass dependency, so you'll correctly read from the input attachment and write out to a new color attachment. So that's not actually how AO in Unreal Engine works, if you're familiar with it. It actually looks more like this. The AO process is actually quite slow, so you don't want to do it full resolution because it's going to bring your frame rate to its knees. It actually downsamples both of these buffers twice before doing the AO, then upsamples it, and then applies it. That's where subpass region comes into play. This is a proposed extension from Qualcomm, working with Kronos. I don't actually know how far along we got with it. But what this allows is the dependency between the subpasses to be larger than the texel and to allow different size subpasses in a single render pass to scale between them. So you can think about creating bitmaps, which is actually perfect if you're going to unify and magnify things. So in pictures, this looks like this. So the existing subpass is basically a one-to-one mapping. You have to take from the source, you have a one-to-one representation. With subpass region, to unify, you can actually take 2 pixels and then have one fragment. So you can see that we can downsample across the board. But we've got this issue now of tile boundaries because we split up the scene into multiple separate tiles. We're going to end up with a line or some kind of like black-in from a tile that doesn't exist because you want to sample from a tile that isn't really there. So you end up with these red, like source image pixels. You have no idea what information they are. This is what I've just sort of discussed. So basically we need to sample from the tile next to it, or what we can actually do is just render those pixels from the other tile again. So you do double the work across those borders. A5X has this gutter region that can actually be configured to render those little pixels outside of the tile. So now we can sample outside of that region. Similar thing happens with Magnify. You can now go up and then you can filter up so you can magnify. So now we can do the entire downsample and upsample AO in Gman and then apply it and then write it out without ever leaving Gman and doing the full deferred opaque pass with ambient occlusion and then write that out. Qualcomm's currently working on the published extension for Kronos, and then it will come out in future driver releases when devices are available. And that's actually me. That's really pretty quick. Are there any questions? I kind of raced through that. Okay, I have those slides. No? Any general Vulkan questions at all? Don't have to be related to the slides. Okay. So now Carlos is going to go back to Vulkan and do a Vulkan capture. You look like you had a question. Concern. Oh, you're right. Okay. Do you want to try this again?
Yeah. Well, I'll just.
Okay. Hello? As you can probably tell, Vulkan is quite complicated. And in Profiler we have Vulkan support. So what I wanted to show you is, I'll still skip over one of the use cases of Profiler that I was going to look at, and we're going to go straight to the Vulkan capture, show the Vulkan profiling capabilities that we have. And hopefully it will ease your transition into the Vulkan world, because it can be quite daunting, especially because of synchronization issues and all sorts of things that you now need to do with that OpenGL did for you previously. So, that is actually, let me bring that back up. So this is the application we're going to be capturing. This is a Qualcomm demo that we have that showcases Vulkan. It's just basically a statue that is fractured, and one of the advantages of Vulkan is to be able to output many more journals than you could do with OpenGL because there's way less driver overhead. So what it showcases here is that it can go from like few journals to like thousands of journals and keep at a good frame rate. So I'm gonna open Profiler up again. And like Dan mentioned, these will be available in future devices, so that's why I had to switch devices on an 820 development platform, or an S7 that could work too. And it's the same drill in terms of like connecting to the device. I just open Profiler, connect to device. I see my MS-7996, connect. And now I open my application and let it load. There we go. So after I finish profiling, you guys can actually look at the application so you can actually see what it's actually doing. But all our Vulkan profiling support right now, it's within the trace mode. We have 2 Vulkan metrics that you can find by finding your application to the Vulkan tab. So it would be the rendering stages, and Vulkan API trees. So rendering stages is going to be pretty much what we just saw in OpenGL just for Vulkan. So we will see what the GPU is actually doing for all the stages within the tiling architecture, but for Vulkan. And Vulkan API trace will be capturing all the calls that actually happen within the capture period. And that way you can better understand how your application is actually being executed. So now that we're familiar with the Gantt track, I won't actually introduce it anymore. I'll just show the different calls that actually happen. You can see them here. If I click on one of them, we can see it in a similar way that we did with draw calls. In the Data Explorer, we can see the calls that actually that were executed. We can see the parameters that were passed, return values. We can see durations, what thread they executed on, etc., etc. One of the more valuable things of this mode is that we get to see all these calls from the perspective of the CPU and from the perspective of the GPU. So this one Gantt track that you see here is what is actually being executed in what we call the host, which is on the CPU on this thread. And then things that actually execute on the GPU, in the case of Vulkan, they're actually done through a submission of queues. So you basically queue your commands and then you submit them. And that actually gets executed in the GPU. So within Profiler, we actually see what happened on the GPU at each point in time. You can see, for example, here, this queue just rendered a lot. And then we just have some correlation helpers just to see what queue submission was actually the one that executed each command buffer. This case is kind of simple because it's single-threaded in terms of the rendering itself, even though the application is multi-threaded because it computes all these things in other threads. But you can see that one of the main issues with Vulkan can be synchronization, like Dan said. And once you start looking into synchronization and multi-threads, you start to get into problems like deadlocking or whatnot. And that's the kind of things that you can actually see here. You can see this example doesn't have it, but if you wait, for example, for something to complete, like Dan said, that it would be a no-no. basically we would see like a very big block that is basically waiting for this thing to finish executing so that it can keep going. So that's the kind of things that you can see from the Vulkan profiling. That's about it for Vulkan. Any questions for Vulkan Snapdragon profiler support? No? Oh, okay. So, what's your name, sir? Develia? Okay. Do you want to pick your keyboard one? There's I don't know what's the third one that you landed. What is this?
That's a Dragon Board development.
Okay, so Dragon Board development board for IoT stuff. I'm assuming, right? Yeah. Beats audio headset or a drone. So, no, this is actually a development board. You can open it and see it. It's sort of like that, yeah, but with a Qualcomm chip. Okay. Well, the guy that was won the other one took off, apparently. Then you can ask the question.
So that's it?
There's two because the guy that won the other one is not here. Well,
Okay.
you know what? His dress is still here, so he might be somewhere.
We'll save it again. Right, so for the, well, at least one, yeah. So for the drone, I'm going to ask a question about my presentation. First hand up and with the correct answer takes home the drone. I think it's actually got a Qualcomm chip in it, right? It doesn't? No? Okay, well we do drone chips, so I thought it might have been. Okay. I mentioned how much faster writing to GMEM was than writing to system memory. Can anybody remember the figure? Yeah, I probably said it really, really fast, so. No?
Tell us the answer and then take it yourself.
Oh, no, not quite. I only had it. Sorry? Yes!
All right.
Man wins a drone.
Yes.
All right.
It's a good guess. The actual answer was 10 to 12, but 10 was, that's yours, yeah. Do you have something you want to ask, Carlos, or should we come up with something else? I'll do another one then. Okay, for here are Beats headphones. Oh. What's the difference between a GL frame buffer and a Vulkan frame buffer? You look like you want to answer.
No?
No?
No, I did hear you talk about it. I just don't know your answer.
Was it the accent?
Let's be fair. Ask questions people like. Don't give me the answer.
Nobody? There's no wrong answers. Just throw something out. Try.
Frames?
Sorry?
Frames?
Frames? No, that's not the answer. Sorry.
That wasn't he's talking about.
Easy question.
I'll defend him. He's doing it.
Easy question.
No, talk about the answer now. So that way we learn.
Oh, okay.
Like this isn't just about giving away stuff. This is about learning stuff.
So the difference between a GL frame buffer and a Vulkan frame buffer. No, not quite so low. The difference is that the GL frame buffer has the attachments just for the current rendering pass. The Vulkan frame buffer has the attachments for all subpasses within a rendering pass. Do you have a question?
I hope this is an easy question.
No, I like the hard ones.
Qualcomm tools, where would you download them from? Or where would you recommend? Developer.qualcomm.com.
You're already good at Mondo.